Alright, nerds, I'm going to get started. So.
I'm not a nerd, I'm Natalie.
Oh, you are a nerd. By definition, you are in here.
I can't math or
If you're in here, you're a fucking nerd.
Alright, guys, so yesterday we finished up talking about angle bisectors, orthogonals, perpendicular bisectors, and medians.
I have a question.
What?
Since I missed part of class yesterday from the ortho, can I count that on my test as absent?
Yep.
I can?
Yep. Now, before you get super excited about being absent, right? All that means is that I wait a week to plug in that 0. That's it. That's it. That's literally it. So, do your best that you can, right, on the quiz, and then maybe you won't get a 0 at all. Or take advantage of being absent, wait a week for the 0 to actually affect your grade, and then come in and get some help, right? The whole point of you being able to write absent on there is that you're going to come and get some help to learn it, and then you can take it, right? It doesn't mean you don't have to take the quiz. Doesn't mean that everything's great. It just means that you don't know it yet. It's not fair for you to have to be graded for it, right? But you need to eventually take it, which is why after a week, if you haven't been to see me or whatever, I do put in the 0, right? That's right. All right, so AE, FB, and DC are examples of what kind of lines? Nope, they don't cut the angles in half. They don't tell us that. Perpendiculars. What's another name for perpendicular? Orthogonal. So these are orthogonals. You can also call them perpendiculars. You can also call them heights of the triangle. You can also call them altitudes. Now, there's a reason I prefer orthogonal, because it helps me remember what the center is when they intersect. What center must that be?
Centroid.
There's a reason I prefer the word orthogonal, even though we can call them heights, altitudes, or perpendiculars. I prefer orthogonal because it helps me remember the name of the center. What's the center name? Mom, braces, bus. Yeah. The orthocenter, right? You go to the orthocenter to get your orthodontics done, right? The very similar. So the orthogonals all intersect at G and create an orthocenter, the center of the orthogonals. That's where the name comes from. Don't memorize this crap. Understand what it means and the connections between it, okay? Memorize the connections. Memorize, right? If I were to make you do this, like, I'm going to write a bunch of crazy symbols on the board. Like, let's do this, and then this, and then this, and that, and like this. No, let's do this. So, those symbols, right? And I was like, I'm going to give you 10 seconds to memorize that, and then you're going to copy it all down, right? I'm going to erase it from the board, and you're going to copy it down, and you're going to be graded on it. That would be cool and unusual. But if you see the concept, it's not that bad. So for this stuff, memorizing it, oh my God, there's so much. Good luck. But if you see the connection, it's much easier. This is really hard to memorize because there's no concept here. Right? It's just a bunch of random crap.
NYC.
But if you know what it means, turn your head sideways. What do you see?
Joe, same thing except sideways.
Z-Y-X-W-V-U-T. It's the alphabet backwards and sideways.
Wait, what?
I just saw the same thing.
Z-Y-X-W-V-U-T, and so on and so forth.
That's really weird.
That's not memorization. Now you see the concept. So if I told you, okay, I'm going to erase from the board, now do it. You could do that very easily. You know how you do it? You'd write it on your paper like this, Z, Y, X, etc., and then turn your paper and say here. Right? Understanding the concept is much easier than trying to memorize a bunch of random crap. You need to see the connection here. Orthogonals, right? They're 90 degrees. They make the orthocenter, right? That makes sense. Don't try to memorize. Yes. Memorization, if you've memorized something but don't understand it, over time, what happens?
Your memory goes away.
Yeah, you forget it. If you understand it, over time, you understand it more. And it gets better. That's the difference between memorizing and understanding. Make sure that you're focusing on understanding. Okay? See the connections. Orthogonal means 90 degrees. That's what those are, right? We can call them perpendiculars. You can call them heights. You can call them altitudes. I prefer orthogonal because it helps you remember that orthocenter. You know the word diagonal, right? Orthogonal is just straight up. It's just another word for a straight line. Diagonals are to the sides, orthogonals are straight up. So those are orthogonals, right? They're 90, and they make the orthocenter. For an acute triangle like this one, the orthocenter is on the inside of the triangle. So we write inside here. Now, what about a right triangle? Don't memorize this crap. Think about it. Here's a right triangle. Now, orthogonals are perpendicular, right? So if you go from like A and draw a line perpendicular to the opposite side, right? That's what you get. That's an orthogonal. So we start at a vertex and draw a 90-degree line to the other side, right? Here's a right triangle. Start at a vertex. Draw a 90-degree line. Isn't it already drawn for you? Isn't this the 90-degree line? Well, isn't this also a 90-degree line from this vertex? Where do they intersect? Katie? Yeah, on the vertex of the 90-degree angle. That makes sense, right? Where's the other one? Well, the other one's less obvious, but it's from here to here. It's the height of the triangle, right? They all intersect at the vertex of the 90-degree. So for the acute, it'll be inside. For a right triangle, well, of course, it's going to be right there, right? We already have the two lines already intersecting there. So it's going to be on the 90-degree vertex. Now, we saw yesterday with GeoGebra, as I stretched the triangle, right, the thing kind of moved back and forth, the center. Well, when the triangle's acute, it was on the inside. And as I stretch the angle more to make it a right angle, it goes from inside to here. So if I keep stretching to make it obtuse, it's going to continue along that path. And where's it going to end up? Outside the triangle, right? It started inside, and as I stretch it to make it 90, it goes to here. And as I stretch more, it's going to send it in the same direction, right? So for an obtuse triangle, it'll be outside the triangle. And the reason for that is because when you draw the heights, the orthogonals, right? That's the height of the triangle, right? This is the ground. There's the height of the triangle from the bottom to the top. You ever seen a diagram like that? Right? And notice that goes outside. Same thing here. If I make this the ground, if that's the ground, right? Do you see it now? That's the ground. If that's the ground, then the height of this triangle is this. And so, of course, they're going to intersect outside. Yeah.
For obtuse, is it always going to be on the outside?
Yeah. For two of our triangles. Some triangles, it's always on the inside, right? It never leaves the inside of the
For
triangle.
obtuse?
For two of our triangles, when it's obtuse, they will be on the outside. But remember, we do have some triangles that always keep it on the inside, right? Right, some centers that always stay on the inside. So for obtuse, for the orthogonal, will be outside. And not just outside, but make sure you know where on the outside. It'll be on the other side of this big angle, right? It won't be out this way, ever. It'll always be, as we stretch it, it continues going that way. Does that make sense? As I go from acute and I stretch it more and more, it keeps pushing it in this direction. Now, special properties, you can write them down, or you can just put it up here. I'm going to put it up here. So notice that these are all right angles, right? Look at line AE and orthogonal BF. Those two orthogonals. Ignore DC for now. Do you see an X? Do you see the X between AE and FB?
Yeah.
If we have an X, we have vertical angles, don't we?
Yeah.
So this angle and this angle are going to be congruent, right, by vertical. Now, I've got a right angle in this triangle and a green angle in this triangle. I've got a right angle in this triangle and a green angle in this triangle. So what do we know about the two triangles? They're similar, right? By AA. Katie, you're on fire. Australia. Rip. Koalas.
I've seen koalas when they're like drenched. in
Notice
water.
that these two are also an X, which means these are vertical angles. So what does that mean about these two triangles? They're also similar. Much like the orthodontist, the orthocenter is kind of boring. Actually, it's really exciting once you like dig through all this, because similar triangles have tons of crazy properties. We're not going to get into it. It's insane. I spent forever 2 nights ago trying to figure out how I would teach you guys that, and I was like, you know what? We're just going to call it. A little too big of a rabbit hole to go down. So these are also vertical, which means these are also similar, right? Now, if you aren't using color, do double squiggles, right? To show that they go together, and then triple squiggles for this one. right? I use color so you can tell which ones go where. But if you're not using color, use like double and triple squiggles. Same thing for your angles, right? Like these pink angles go together, but if they're not in color, you wouldn't know they were pink. So you use like double bars. And these blue angles, you could do triple bars. So even when it's not in color, you can tell what goes with what, right? The triple bars go together, the double bars go together, and the single go together. You cool with that? Make sure you do that, because otherwise it looks like all the angles are congruent and all the triangles are similar, and that's just not true. These two are similar to each other, but these two are not similar to each other, right? These two go together. And that's all the special properties of the orthocenter. Orthogonals, 90 degrees, right? It's not diagonal, it's orthogonal. Orthocenter. Orthocenter is on the inside for acute. All of the triangles, when they're acute, will have their centers on the inside, always. For a right triangle, well, we already have two orthogonals drawn for us. They intersect there. Shocker. And then these heights are on the outside, right? So they end up here. Cool with that? Maybe you're not 100%. I feel like this stuff isn't hard. It's just a lot, right? So you're going to need to study for this quiz. You will. Again, focus on the connections, the ideas, why things are what they are, so that you're not just trying to memorize a bunch of random crap, right? 2. What kind of line segments do you see here? A, E, F, B, and D, C.
Medians.
Medians, yep. Medians are vertex to midpoint, right? How do we know? Well, A is definitely a vertex, right, of a triangle, right? That's no question. How do we know that E is a midpoint?
Two shared.
Yeah, it's cut in half, right? Where is the stapler? Oh, you got it? Okay. Yep, so we do know that's a midpoint. And that's a midpoint, that's a midpoint. So vertex to midpoint, these are medians, right? Now, if you're like me and learned all of your math online from Eastern Europeans, because I'm a real math teacher, totally am. I'm only short like 4 credits. It's totally fine. You'll know that the center that they make is called the Medicenter, right? Now, outside of the Eastern Bloc, so in the U.S. and Western countries, we call it something else. Does anybody remember? The centroid, right? So it is your God-given American right to use a different name than the rest of the world, much like feet versus meters, right?
What you talking about? You're talking about
George Washington
No.
just had a foot fetish.
Right?
Fair? Makes sense.
Medicenter makes sense because medians. The intersection of the medians is the medicenter. The intersection of the orthogonals is the orthocenter, right? But America's like, no, centroid.
What's wrong with America?
You know, I ask myself that every day. So, that makes sense. You can call it either. I'll probably call it the Medicenter. That's just how I learned it. Again, I learned my math online
This water tastes gross.
because I like watching YouTube and learning cool new things.
Can I refill this?
All right, yes. So we also know, again, you can write it down at the bottom, but I'm just going to write it next to the diagram. The Medicenter, or the centroid, that's the center of mass, right, of the triangle. It's the balance point. All except either center of mass or balance point. Now, if you find a balance point on an object, right, for different objects, it's in different spots. If it's perfectly balanced, it'll be right in the middle, right? But if it's heavier on one side, then you got to lean towards that side, right? It's hard to find. But will the balance point of an object ever be outside the object? No, no. Like, how are you going to balance anything like this? Oh man, I'm real bad at this, right? So when I ask you, where will the center of mass be on an acute triangle? Inside the triangle. Where would it be for a right triangle? Well, somewhere inside the, and where will it be for obtuse? Somewhere inside the triangle, right? I don't care what object we're talking about. Doesn't matter if it's a triangle. It'll always be inside. Again, lots to memorize unless you see the connections, right? It's the center of mass, so it's always inside. How could it be anything else? And once you start feeling like that, you'll feel better, yeah?
Can you explain the obtuse?
Mm-hmm. So it's always inside because it's the center of mass. And remember, the center of mass is the balance point. And the balance point on an object will always be inside the object. Like on this pen, the balance point is like right here.
And you know it's the center of mass?
Yep, because that's what the Medicenter is.
Oh, okay.
Right? So of course it's always inside, right? You never have a balance point outside the object. Cool. Now, there's also one other property that the medians have. The Medicenter cuts the median into 2 pieces, right? So AG and GE. And those pieces are special. They're related in a certain way. So AG will always be twice as big as its counterpart, GE. They're in a 2-to-1 ratio. So maybe it'll be like 6 and 3 or 10 and 5, right? But it's always 2-to-1. Same thing here. If this was 7, this would be 7 halves. Let me choose a better example. Let's choose an even number. If this was 16, what would this be? 8. That part would be 8, right? They're always related 2-to-1. We proved that last week. You just don't remember because we didn't call it medians and we didn't say medicenter. We just did proving triangles similar. And we got a 2-to-1 ratio. On ours, we didn't have this big line drawn in here, but we did have this drawn across, and we used that to prove the triangle similar, and then these were 2-to-1. But you don't remember that, it's okay. We'll prove it again next week. So that's the special parts about the medians, right? They make the medicenter or centroid, which is center mass, which is always inside the triangle. And they cut the triangle into 2-to-1 ratio. How do you feel? Yeah.
Do we have a decimal?
It'll look just like this. Orthobus. Yep. Although I think it's very doable. Yeah.
Wait, so for the any special properties, so like for that one, like where do we like mention that?
You can write it, or you can put it in the diagram, like I did for this, right? Or for this.
So like what would it be, like the first and second one? Like what would it be called?
I would say AG over GE equals this. So I'd say like AG over GE is a 2-to-1 ratio.
Okay.
Right? And you can show that for all of them. I won't make you draw it for all of them. Doing it for one is enough for me, yeah.
So how do you know that it's a median?
Medians are always vertex to midpoint. So yeah, that's definitely a midpoint.
Okay.
Yep. Vertex to midpoint. I'll write that down on here. Vertex to midpoint is a median. Orthogonals are orthogonal, right? Go straight up, they're not diagonal. Vertex to midpoint gets you the median, right? All right, let's look at number 3. What kind of lines do you see here? What are those lines doing to the triangle?
Dividing the angles.
Yeah, it divides angles in 2. What do we call that?
I don't remember.
Angle bisectors, right? Bisect means cut into 2. These are angle bisectors. Now this one's kind of weird, right? Median, medicenter, orthogonal, orthocenter. The angle bisectors intersect at what's called the incenter. Now we call it the incenter because it's the center of what?
The inside.
Of,
Mass.
nope, that's centroid, right?
Yeah.
Inside the center of the triangle.
There's a hidden circle here,
What?
and it's inside the
yeah.
triangle. Remember that? So, turns out that G, if it's the incenter, will be the same distance to every side of the triangle. It's equidistant to every side. Now, when we measure distance, we measure perpendicularly, okay? So if I want to measure how short I am compared to the ceiling, I'd measure straight up, right? I wouldn't measure to the side. Right? If I want to compare my height to Mark, I wouldn't stand back to back and go like, look, we're the same height, right? I'd go like this, and I'd be like, yeah, I'm shorter, right? So when we measure from G to the side, we don't just pick any line to measure, right? We pick a line that's perpendicular to that side. Does that make sense? Right? That's how we're going to measure. So from G to the opposite side, we measure at a 90 degree. And from G to this side, we measure at a 90 degree. And when we do that, if G is the incenter, which it is because those angle bisectors tell us it is, then we know that G is the same distance from every side. So these sides, these segments I drew will all be the same length. Okay. Now, if we have a point and we draw lines from it that are all the same length, what do we end up with? If we have a point, we draw lines from it that are all the same length, what do we end up with?
Circle.
A circle, right? So there's a circle here. And the circle is inside the triangle. That's why we call it the incenter. So let's draw our circle inside the triangle. It's going to connect all these points up, right? Our radii.
It looks like a peace symbol.
That bottom kind of sucks. The rest was pretty good. All right. And we call that an inscribed circle. In meaning inside, scribe meaning to write, right? So inscribed, written inside. An inscribed circle. Cool. So I do need that word written down. Don't just draw the picture, tell me what it is. It's an inscribed circle, which is why we call it the incenter, right? The incenter is the center of that circle, inside the triangle. Now, if the incenter is the center of a circle that's inside the triangle, circle's inside the triangle, right? no matter how I stretch that triangle, the circle's always still in the triangle, right? That's why it's called inscribed. So will the center of that circle ever be outside the triangle? No, right? The circle's inside the triangle no matter what you do. That's why it's called inscribed, right? It's inside the triangle. So its center will never be outside the triangle, right? Here's the circle. Its center's right there. If it's in the triangle, so is the center. So it's always inside. And that's that on that. Again, we knew these are angle bisectors because it cuts these angles into half, right? And where they intersect makes G, and that's the incenter. And the incenter is the center of an inscribed circle. And if we have a circle, we should have radii to the outside of the triangle. Right? The edges. 4 is the weirdest one. You might think, oh, look, a median. Look, that's midpoint, and that's A. Okay? But what is it better described as? Because not all of these go to the vertices, do they? We've got 90 degrees. So they could be called orthogonals, but what are they really? Perpendicular bisectors. Perpendicular because they're perpendicular. Bisectors because they cut the sides. If they cut the angles in half, what do we call that? Angle bisectors, right? So when we say perpendicular bisectors, we mean perpendicular lines that come from the bisection of the sides, otherwise known as the midpoint, right? So midpoint straight up to 90. So we're going to call those perpendicular. Perpendicular bisectors. That's a big one, right? Now, G, unfortunately, much like the incenter and the angle bisectors, right, doesn't have a really catchy name that helps you remember. Like orthocenter, orthogonals, right? And midpoint, or medicenter and medians, right? Perpendicular bisectors intersect at the circumcenter. Now, if you go to the orthocenter for your ortho needs, what do you go to the circumcenter for? Circumference. Very good. So circumference means to like go around the circle, right? The circumference. Careful how you say that one. Okay. So we have a circumscribed. Again, careful how you say it. Circumscribed circle. Okay. Now, just like Magellan, he circumnavigated the world, right? We're going to go all the way around the outside of the triangle. So around the outside of the triangle, we have a circumscribed circle. That's right, Ferdinand. Ferdinand's a great name. Ferdinand Archibald, right? It was Franz du Ferdinand. Right? Franz Ferdinand, the punk band, named after Franz du Ferdinand, that was assassinated to start World War I. Yes, that guy too. It's not Fernando. It's Ferdinand. There was a movie that was made for it that nobody watched. So we have a circumcenter and, oh, whoops, sorry, I didn't mean to write circumcenter. We wrote that down here. What I meant to write was a circumscribed, scribe means to write, size means to cut, circumscribed circle. Right? Oy vey. I feel like I should wear my yarmulke tomorrow.
Do it, please.
It's a Jewish ceremonial religious hat. I am not, no. But I went to Passover a couple years ago with a friend, and they gave me a yarmulke. Now it's in one of my suit jackets. I can't remember which one. I'm always prepared. That's rad.
I'm not Jewish.
Wait.
Nice.
All right, so if we have a circle, we should have radii.
There's one easy way to
Now,
tell you guys Jewish.
Is the radii going to be from G to a side of the triangle? No, that's not the radius of the circle. It's going to be from G to what? All right, guys, shut up. Guys, shut up. So, if we have circles, right, there should be radii. Going from the center to the circle will be a radius. Now, I could draw a radius anywhere, right? But the interesting one is here, because C is on our circle, right? Or at least it is if you draw it right. And G and B will be a radii, and G and A will be. Now, notice that this angle bisector looks like it hits A. Even if it does, right, the angle bisectors aren't always going to be the same thing as the radii. This one's just slightly different, okay? It's to the side of it. Oh, let's do 4. Right? So G is equidistant from the vertices, right? So if you go from each vertex in the same amount, you'll find G, the circumcenter. Whereas with the incenter, Where's the in-center? In-center. It's the same distance from the sides, right? So in-center is equidistant from the sides. Circumcenter is equidistant from the vertices, right? And that makes sense because the circle goes around and the vertices are on our circle, right? Whereas the in-center, the circle goes inside and the vertices or the radii are on our sides, right? They go to the sides. The sides are on our circle. So make sure you draw in your radii. I do need to see those. Okay, cool. Turns out this creates a lot of congruent triangles, but we're not going to worry about it. Yeah.
Can you go back to problem 1?
I'm going to go back over all 4 in a second. Yep. So when it's acute, it's inside, right? That's an acute triangle. It's inside. Now, think about it. If I make a right triangle, G is supposed to be the same distance from every vertex, right? Right? So let's go to the vertex of our right triangle. The same distance from every vertex is going to be right here. Right?
Yeah.
So it's going to be on the midpoint of the hypotenuse. So that's where G will be, on the midpoint of the hypotenuse, because it's the same distance from every vertex. So midpoint of the hypotenuse, hypoponymous.
I want to join the hype house. Do you think I can?
Oh, of course.
I have what it takes. I have perfect teeth.
Now, acute, it's on the inside. As I stretch that angle to make it a right angle, it pushes it this direction. Ladies, I'm doing this because you'll cry tomorrow, and this will save you from tears.
I don't cry.
Okay? You do on the inside. We have Kleenexes just for tomorrow. Okay? So, acute triangle, it's on the inside. As we stretch that angle to make it a right angle, it pushes the point, the center, to here. If we keep stretching that angle, it's going to keep pushing it out, right? So for an obtuse triangle, it's going to push it out to here, outside. Also, ladies, if we end up not getting through this because I keep having to stop and tell you to shut up, the rest of the class will hate you if they don't already.
They are.
All right, great, wonderful. So, outside. Now, not outside behind, right? Outside out front. This angle gets bigger and it pushes it out that way, just like this pushes it out, right? We go from acute to making that angle bigger, it pushes it towards there, and then we make it even bigger and it pushes it even further out. And the reason for that is because, again, we have a circle that hits all the points. So that'll be the diameter. And then to make a circle out of this, I'd make a really wide circle, right? Which is why I get that center. Yeah.
Never mind.
Okay.
Couldn't you still have it on the other side because you can make a circle like as with the long side as the bottom?
So remember, the circle connects all 3 points. So if I connected these like this, I wouldn't be able to hit that one, right? It wouldn't be a circle, right? Good question. All right. So that's that on that. I'm going to go back and do them again, 1 through 4. And then we're going to move on to the rest. Number 1. I know those are orthogonals. How do I know that those lines are orthogonals?
Because they have the 90 degrees.
90 degree, they're orthogonal. They're not diagonal, they're orthogonal, right? And the orthogonals intersect at the orthocenter, because that makes sense, right? It breaks it up into a bunch of similar triangles because we have vertical angles, right? And then we know that the orthocenter is on the inside for an acute, on the 90-degree vertex for a right triangle, because these 2 lines are orthogonals, right? Those 2 lines on your triangle are orthogonal, right? And then it keeps pushing it in that direction from here to outside, right? As we widen that angle. Does that make sense? How it slides out? Right? 2. How do I know that those are medians? Yeah.
Vertex to midpoint.
Exactly. We have vertex to midpoint. That's a midpoint because by definition it is, right? So we have medians. Medians intersect at the medicenter or centroid. Again, God give them right, whatever you want to call it. Okay. And the centroid divides up the median into a 2-to-1 ratio. So if that's 2 and that's 1, maybe that could be 6 and 3, maybe that could be 8 and 4, right? They're always a 2-to-1 ratio. Now, the centroid is also known as the center of mass, right? Medicenter, centroid, center of mass. And will the balance point on an object ever be outside it? No, so it's always on the inside. 3, angle bisectors, because it bisects the angles. That's a tough one. It bisects the angle, means it cuts it in two, right? So those are angle bisectors. Where they intersect is called the incenter. There's no real connection there. Well, we call it the incenter. Why? Why do we call it the incenter? Yeah.
Because it's the center of the inscribed circle.
Exactly. Inside circle, inscribed circle, right? That's why we call it the incenter. Now, when we measure from here to the outside, the sides, right, we always measure at a 90-degree angle, right? We don't measure to the side like this. That'd be weird, right? From me to the ceiling, I'd measure straight up. So when I measure out to those sides, I get 90 degree, and it'll be the same distance to all sides. Now, will this ever be, that center ever be outside the triangle? No, because the circle's inside, so it's got to be inside always, right? Number 4, circumcenter, perpendicular bisectors. How do I know they're perpendicular bisectors? How do I know that, like, DG is a perpendicular bisector?
It has two shared
Congruent sides, yep.
Two congruent sides and 90 degree.
Yeah, exactly. It bisects the side, and it goes there perpendicularly, right? It's a perpendicular
Is it
bisector.
inside when it's obtuse? I didn't get that written down.
Yes, it's outside when it's obtuse, and I'll show you why. So we call this the circumcenter because it's the center of what? What kind of circle? Remember, the word scribe is in there because we have to write or draw. Circumscribed, exactly. Careful how you say that one. A circumscribed circle, right? Circumcised, size means cut, right? Circumscribe means to go and draw, right? So it goes around the triangle, which means the distance from G to A and G to C and G to B are radii, right? Which means they're all the same. Now, when it's acute, it's inside the triangle, right? Because that makes a circle. So, Andrew, this is for you. This makes a circle that goes around the triangle, and the center, of course, for an acute triangle will be inside, right? For a right triangle, remember, it's always the same distance from our vertices, right? So if I go from my vertex to here, and vertex to here, and vertex to here, that's all the same distance. So it ends up being at the midpoint of the hypotenuse, which makes this the diameter of the circle, right? So the center will be right on the midpoint of the hypotenuse. As I stretch that angle bigger, it keeps pushing it from inside to on to out. It keeps going in that direction, so it ends up in the outside here, okay? And that makes sense, because if I try to make a circle with all those 3 points, I'd make a really big circle, and that's where it'll be, right? How do we feel? Maybe not 100, but you will after you study, right? Do we see the concepts now so we can see them later when we study? That's the key. Okay, let's look at 5. Now, 5, they tell you that G is the circumcenter. Why do we call it the circumcenter?
Circumscribed.
Circumscribed circle, so let's draw our circumscribed circle in. Now, what lines make up the circumcenter? What lines connect to make the circumcenter? It's one of the weird ones. Well, it's not the orthogonals, right? It's not going to be the medians, right? It's either the angle bisectors or the perpendicular bisectors. Perpendicular. So what we're going to do is we're going to find our midpoints on all the sides, right? Just, estimate. And we should be able to draw a perpendicular line from the midpoint, starting at the midpoint, not the vertices. And it should go straight through G, right? So this line right here is perpendicular. So that's a perpendicular bisector. We good with that? I can do that for all of these. So that's a perpendicular bisector, right? This should also be a perpendicular bisector. And this should also be a perpendicular bisector. Again, drawing from my midpoint through G, 90 degrees. It does not necessarily connect to the vertices. See, I'm not connecting it to B. A lot of you guys are going to get brain farts tomorrow when you try to connect these to the vertices. They don't. They just go off in whatever they want to do. Okay? So those are perpendicular bisectors. Cool. Now we got to add radii because we have a circle, right? Don't forget to add your radii. So, is it going to be from G to the sides that's the radius? No, right? The sides aren't on the circle. It's going to be from G to what? G to the, what do we call these? G to the what? Starts with a V.
Vertex.
Vertex, or vertices, plural, right? So from here to here, and here to here, and here to here will all be the same distance. Because they're radii, right? Are you following me?
I'm trying.
Okay. Macy, you're doing great. You weren't here yesterday, but you did your best. Okay? I'm going to move to the orthocenter. What lines make up the orthocenter? Come on. What lines connect to make the orthocenter? The 90 degrees, the orthogonals, right? So all we have to do is start at the top of our triangle and draw our heights in, essentially, right? So I'm going to draw a line through here, and that'll hit 90. Right? Remember, orthogonals are the heights of the triangle. It might be easier to rotate the triangle and be like, okay, now that's my bottom, right? So the height would be from here to here. So that must be 90. And then the last one I can draw in like this, with that being the bottom. So it's going to go from B through G down to the bottom at 90 degrees. Does it cut those sides in half? Maybe. We don't know, right? Probably not, though. So those are the orthogonals. So we'll write that down, orthogonals. Now, much like the orthodontist, there's not really a whole lot of exciting stuff to add, like with the circumcenter, right? We ended up with like this Frankenstein diagram, right? Orthocenter, we just have vertical angles, which means we have similar triangles, right? These two are vertical, so these two are similar. These two angles are vertical, so these two are similar. And these two angles are vertical, so these two are similar, right? Because the vertical angle is the second angle in the triangle that matches, right? We've got a right angle and a blue angle. We've got a right angle and a blue angle, so they must be similar by double A, right? Better? Again, the reason they're similar is because we have a right angle and a blue angle in both of these triangles, so they must be similar by double A. A right angle that I didn't draw in, and a green angle, a right angle and a green angle, they're going to be similar. A right angle that I didn't draw in and a pink angle, a right angle that I didn't draw in and a pink angle, right? So they're going to be similar by double A. So we have orthogonals and we've got similar triangles, right? That's it. And then all the properties that similar triangles bring. In center. Why do we call it the in center?
It's in the center of the triangle.
Yeah, well, I mean, we have lots of different centers of the triangle. We have 4 different ones. Yeah.
Center of an inscribed circle.
Good, there should be an inscribed circle here. Now, that means it's the same distance from every side. So I'm going to draw from here to here 90. Remember, because we measure things at 90 degrees. From here to here looks like 90. And then this one's pretty easy to figure out. From here to here is 90. Again, we're trying to measure consistently, so we always measure to 90 degrees. And these will all be radii, so they're all congruent. So those are my radii, right? Remember, the in-center is always the same distance from every side. But we must have a hidden circle here, a secret circle. And it's an inscribed circle, so I'm going to connect all these up. Yeah! That's pretty good. Best one today. All right. Cool, cool, cool. Now, we forgot. What segments actually make the in-center? Like, what segments do we connect up to make the in-center? Obviously, the same distance from every side, but... Nope, not orthogonals. That's the orthocenter. It's one of the weird ones, right? Medians make the medicenter. Orthogonals make the orthocenter. We already said perpendicular bisectors make the circumcenter. It's the angle bisectors. Angle bisectors make this guy, okay? That one's kind of weird. You wouldn't expect, like, let's draw some angle bisectors, and then all of a sudden, oh my god, it's the perfect point that's the same distance from every side, right? Seems pretty random. But it's true. So I'm going to draw in all my angle bisectors, which means this angle's cut into 2 pieces, right? This angle will be cut into 2 pieces. And let's use red. Now we'll use red. This angle must be cut into 2 pieces if I connect C and G. And again, I draw it straight through the triangle because it doesn't hit any special point on the other side, right? I just keep drawing. With orthocenters, I had to stop because they stop at the 90, right? For this, I just kept going. So it's key to show those are cut in half, so we write angle bisectors. And what kind of circle is that? What kind of circle? Inscribed, because it's the in-center, right? It's inside. We have an inscribed circle. Cool. The angle bisectors make an inscribed circle with the center being the in-center. Ocho. Centroid or medicenter, whichever one you want to call it. What lines make the medicenter? What do we call those? There's a reason I like calling it the medicenter. Medians, right? It's like range, median, mode, mean, right? Mean, median, and mode. Median. Now, how do we draw a median? It's vertex to what? Yeah, midpoint. So let's find our midpoints. Call that a midpoint. We'll call that a midpoint. Make sure you mark your diagram so I know that they're midpoints. And now we're going to connect vertex to midpoint. Boop. Vertex to midpoint. These are the fun ones to draw, I think. I went too far. Oops. He's gone too far. I went too far again. My bad.
Nobody Logan Paul.
Now, what do we know about G and how it cuts up the medians? It cuts up the medians into what ratio? Not half and half, right? But what? 2 to 1, exactly. So if this is 2, its counterpart would be 1. So we got medians, we got midpoints, and we got a 2 to 1 ratio for the segments, right? If GB were 8, how much would G to this be? 4, right? That's the idea. Take a look at 9. Good God! All right, so what kind of lines are those that I drew? Look closely. What kind of lines are they? Well, they're definitely perpendicular, so they're either orthogonal or what? Perpendicular bisectors. Are they perpendicular bisectors? Yeah, right? Look, they're equidistant here. Those are midpoints, right? So these are perpendicular bisectors. Now, if those are perpendicular bisectors, and they is because they're perpendicular and they bisect the side, right? What's the center of the perpendicular bisectors? What center is that?
Obtuse.
That's not a center name. That's a triangle name.
Circumcenter.
Circumcenter, yep. So G must be the circumcenter. Now, why do we call it the circumcenter? Because you go there for all your circumference needs. So there should be a circle somewhere. Where it gonna be? Well, duh. I mean, if the center of the circle's on the outside, right? And we connect up all of our vertices, right, on that circle.
Damn.
So we're gonna have a real big one.
Dude, you're big.
That's what she said. All right. Marissa didn't say it. I had to. All right. Now, if we have a circle, we should have what? If we have a circle, what should we have? What do all circles have?
I think that's myself.
Centers, and what else? Radii, radius, yep. So the radius of this circle is like G to A or G to B or G to C, right? Those are all going to be radii, which means if they're all radii, what's true about their lengths? They're all the same, right? So we know from G to B and G to C and G to A is all the same distance, right? They're all going to be radii. It's gross looking, right?
What are radii?
Plural of radius, like a radius of a circle.
I don't like brother. My brother goes as far.
So here's a circle. The distance from the center to the outside is a radius, right? And radii is plural of that. So here's 2 radii, right? And if you connect up 2 radii back to back by 90-degree angles, we call that D for diameter, right?
I think I should learn that.
So those are radii. Plural of radius, okay? Radius is always the distance from the center to the outside of the circle. Notice that those 3 points are on the outside of our circle, right? Let's look at 10. Ew, gross! What kind of lines are those? The triangle is ABC. I know there's a lot of triangles here. Focus on triangle ABC.
That looks 90 degrees.
What kind of line is that? It looks 90, so it's perpendicular. Is it a bisector as well? They don't tell us, right? So all we can assume is it's a perpendicular. So we call those what? Starts with an O. Orthogonals, right? So we have orthogonals, which means G must be what kind of center? The orthocenter. Grace's bus. So G is the orthocenter, which means we should have similar triangles. Well, I think you can see that these two triangles have vertical angles, right? Here and here. So these two should be similar because we have a 90-degree angle in this triangle and a green angle, and we have a 90-degree and a green angle, right? So they're going to be similar. The other two will be similar, but you probably don't see why or how. So we're going to leave that. I won't mark you down for not marking all of the similar triangles. Okay, these two will be similar, but I don't think you guys know how to prove it yet. There's no vertical angles there, right? It's a little bit harder. Let's look at 11. We'll worry about that next week. They don't give us a lot of information,
Oh, that looks wonderful.
but they do tell us how long these little bits are, right? What do you notice?
I don't think I got the one.
Oh, they're 2 to 1.
They're 2 to 1, which means those must be
Medium.
medians. Yep, we have medians,
I didn't get an 11 or a 12.
which means means are, or medians connect at what? What do they connect to?
Medicenter.
The medicenter.
Or the centroid.
Yep.
There it
You didn't get what? Oh, you didn't get it. You didn't receive it. I understand. I was so confused. Like, we haven't done it yet, so I wouldn't expect you to. Like, I don't understand. 12? Macy, you need to calm down. We're not even there yet. Okay? And so notice it's a 2 to 1 ratio. So now, medians. They're vertex to what?
Or,
Mid.
Midpoint, which means this must be a midpoint. So mark it as such. Vertex to midpoint, right? If they're medians, they have to be. So this must be a midpoint as well. Yay! And of course, the 2 to 1 ratio they already gave us, right? 12.
perpendicular bisector.
Nope. Misleading. They are perpendicular.
Oh.
But guess what? Are those the heights of the triangle?
No.
No way, Jose! Okay? But it shows that G is the same distance from every side.
Are those all orthogonals?
Nope. Orthogonals are the height of the triangle. They're not heights.
Bisectors?
Nope. They don't bisect anything, especially angles. It shows that G is the same distance from every side, which means this is the in-center. Those are radii, which means we have angle bisectors here, here, and here.
Mac, I modified the notes.
See you tomorrow for your quiz.
Look at what I did. I modified
Rad.
it so I could understand it and so I could have more things. Hell yeah. Still a failure.
Watch the video to review.
Andrew, don't worry, you're not the only one.
Again, these angles get cut in half because those must be angle bisectors. Bye, Macy. Hello.
Isn't the Ice Age like 18 years old now?